Okay, so I need to be careful to save time. So I'm going to jump to slide 7 to define, to remind you, because obviously you have seen these things before, to define what is an eigenvalue problem. So we are looking for these scalars lambda, which we call them the eigenvalues, and these vectors x, so that ax equal to lambda x. And obviously our interests are to find non-zero lambdas and non-zero x, okay? But this is what we call an eigenvalue problem. So given A, to find lambda and to find x. All right, so I will keep going, all right? So we're interested, I see ahead on my slides. Not very good. So we're, the set of eigenvalues is called the spectrum of the matrix A. And you may have seen things in later courses, maybe numerical methods, spectral methods. Everything that has the word spectral on it has something to do with eigenvalues and eigenvectors, okay? Practically, actually, I do not know any method in science and engineering that uses computers that does not involve either in execution or in theory eigenvalues and eigenvectors. There is really, you're going to have a hard time to convince me there is any subject area that doesn't involve eigenvalues and eigenvectors, okay? So when you were taking dynamics courses, you were learning about the modes of vibration, the modes of this. What do you think are those? They're eigenvectors, right? So they're eigenvectors. Maybe eigenvectors and eigenvalues not of a matrix, but of some differential operator. But the differential operator, if you discretize it, you get a matrix. So eventually everything goes down to solving ax equal lambda x. So the set of eigenvalues is called the spectrum of A. And the largest of the absolute values of the eigenvalues is called the spectral radius. I am not going to make use of this extensively in this course, but it is of extreme importance in stability analysis. So when we discuss later on differential equations and dynamical systems, you will see that this is coming to be a very important concept. So the stability of calculations will depend on the spectral radius of the underlying matrix A. All right, so let's do a simple example. We actually have all the machinery we need to solve ax equal lambda x, okay? So A is a simple 2 by 2. So we need to solve this eigenvalue problem. So can somebody remind me, how are you going to solve this? Based on what we learned up to now, so if you rearrange this, right, and you will see the equation, you can write this A minus lambda I times x equal to 0. And what type of problem does this matrix times x equal to 0 reminds you? How do we call the null space? So effectively, we're looking for non-zero solutions to the null space, not of A, but of A minus lambda I. And to get non-zero x's, the only way that can happen is if the matrix A minus lambda I is singular. And one of the things, maybe it was not emphasized too much when we were discussing about determinants, but you already know this because the determinant is the product of pivots and in all the nice properties. A minus lambda I is singular when the determinant of A minus lambda I equal to 0. So basically the idea here is compute the lambdas by taking the fact that A minus lambda I has to be singular. And then once you find lambda, for each lambda, compute the solutions to the null space problem A minus lambda Ix equal to 0. Okay? So everything we discuss about computing the null space, and that is going to be in the exam also today, okay? Because it's a fundamental problem. So that will tell us what the eigenvectors are for a given eigenvalue. So, all right, so this is the A minus lambda I problem. This is written in a more compact form. This is really how we're going to be using it, but you can see here for the 2 by 2 case explicitly. We subtracted lambda times the identity matrix from A. So you're going to take the determinant equal to 0. This is the characteristic equation or characteristic polynomial, whatever you call it. And you notice because the matrix is 2 by 2, this polynomial is of the order 2. Okay? So actually, again, mathematics come in a very strange way, right? You see polynomial theory, computing roots of polynomials, comes to play a role here. Because if you have a problem with a matrix A that is 1 billion by 1 billion, and you have to find all its eigenvalues, you are ruined, right? Literally, you cannot do it with any method. But you know, lots of problems in practice, somehow, and maybe if I have time, I will demonstrate today, you will see that you may not need all the eigenvalues, okay? Because somehow, for the type of things you want to do, some seem to be, as we will see, sort of to die out, okay, when you do operations in the type of things we want to do. Hopefully in the lecture today, I think I have an example, so I'm going to show you this. But in this case, is 2 by is a square, is a quadratic polynomial. We can actually solve it, and it has 2 roots, -1 and -6. This is very nice. So we have 2 distinct eigenvalues, and I can tell you so I don't forget it. If you have 2 distinct eigenvalues, and in this case they are real, there are also 2 distinct eigenvectors as well, okay? And actually there is a theorem that I will demonstrate how you prove it. So you are going to take lambda 1 equal to -1, and then you're going to compute the null space solutions to A minus the -1 I, right? That's our matrix that comes in the picture, so we're going to compute that null space. So this is the problem. We're going to plug in lambda 1 equal to -1, and we're going to compute x1 and x2. And you can see, because this matrix is singular, the 2 equations are basically multiples of each other, right? You can see that. I mean, actually, if you don't get a singular matrix when you calculate eigenvalues, you know you have done something wrong, right? I mean, by definition, basically, you have done something wrong. So immediately, you can see that one of the solutions of this problem can be, you can take x1 equal to 1, and then x2 is equal to 2. So any vector in that direction will actually be in the null space. That's a very simple problem. And let me see if, OK, so this is the first eigenvector. And you can actually test it. If you multiply A by this eigenvector, you actually get, as we have written like this, actually, -1 times x1. All right, and x1 is 1 and 2. So this is indeed the correct eigenvector. But the way you can appreciate when you compute these eigenvectors, if I go on this equation, right, and instead of x1 being 1 and 2, if I use x1 to be 2 and 4, that is still an eigenvector. So effectively, to be able to communicate with each other when we say here are the eigenvectors, it's easier if you normalize them, right? So you don't have a different eigenvector from me. Just normalize them, so at least we get the same answer. All right, so we can plug in now lambda 2, and you can immediately see that if you set x, let me see. If you set x1 equal to 2, then x2 is -1. And so this is my second eigenvector, and actually you can verify ax2 is -6 times x2, right? -6 is my eigenvalue. All right, so let's do this example now, okay? I don't know why, I'm sure if there is an example, it must be something different with this case that I need to do so I don't repeat myself. So we have this nice matrix. So we calculate the eigenvalues of this. So we take the characteristic equation, the determinant equal to 0, and it has 2 eigenvalues, lambda equal to 1 and lambda equal to 1/2. So we now have to compute the null space of A minus I and A minus 1/2 I. All right? So you can actually show that the two eigenvectors are 0.6, 0.4, and 1 minus 1. Okay, don't have to do the algebra. You can verify in a few seconds in a piece of paper that these are the two eigenvectors. And actually here is the verification. AX1, if you multiply them, you actually get x1 because you can see lambda is equal to 1. And AX2 is 1/2 x2. So what I want to emphasize is the following, right? So AX equal lambda x. So if you have an eigenvector and you operate on it with the matrix A, so an eigenvector of A, and you operate on it with A, the new vector that you get does not change direction. You see that? These are spatial directions. So if you operate A on an eigenvector, you stay in the direction of the eigenvector. So in this particular example, if you operate A on the first eigenvector, because the eigenvalue is equal to 1, you are in the direction, you're in the x1 direction still. If you operate on x2 with A, you're still in the direction of x2 times some scalar, but you're still in the direction of x2. So the direction doesn't change. Now, how about if I keep operating with A on an eigenvector, and I take A square of x1, right? So if AX1 is x1, how much is A square of x1? Do the operations on the eigenvector one at a time. So A squared is A times A. So A squared x1 will give you what? A operating on AX1. And AX1 is what? Because the eigenvalue is 1. Is x1. And what is AX1? Is x1. So effectively, if you keep operating with A, you remain in the original direction of these eigenvectors, regardless of what power of the matrices you take. And actually, we will use this trick to compute A to the power 900. All right? If you try to calculate A to the power 900 by multiplying things, or if you put this in MATLAB and you say, can you please do this for me? And you keep writing A times A times A times A, how many times I put in, MATLAB is going to come back and say, we don't want you as a user. Okay? Because this requires this idea with eigenvectors and eigenvalues. Okay? All right. So, I want you to remember geometrically that these eigenvectors are special vectors that somehow keep their orientation when you operate on them with A, right? They are special directions. They are special directions. All right. Now, let me jump in now. Every other vector obviously is not a special vector. We only have the eigenvectors, right? So I am still using the same example that I did, the 2 by 2, with the two eigenvectors x1 and x2 we computed. All right? So let me take an arbitrary other vector in R2. So this is a vector 0.8 and 0.2. It's not an eigenvector. So I'm going to show you a little trick that we will need to use actually all the time from now on how to operate on this vector simply by knowing how to operate on eigenvectors, because eigenvectors maintain their orientation. So you know what I'm going to do is, for this particular case, because I have two independent eigenvectors, they span the whole of R2. Can you see that? Because the matrix inverted, they span the whole of R2. Okay? So these two eigenvectors can actually, by combination, can generate any other vector in R2. So what I can do is, I can take this vector 0.8, 0.2, just some arbitrary vector, and I can write it as x1 plus 0.2 x2. I can write as a combination of the two eigenvectors. All right? And I forgot, what are the two, if we can go back, right? Anybody remembers? OK, so remember, x1 is 0.6, 0.4, and x2 is 1 minus 1. OK? Somebody write down 0.6, 0.4, 1 minus 1. OK, 0.6, 0.4. So 0.6, 0.4, 1 minus 1 times 0.2 gives you that. So you can see this is 0.8 and 0.2, correct? All right. So somebody will say, can you tell me what is the effect of operating with A on this vector? And obviously, because it's a trivial example, you will multiply A with that vector and say, this is it. But let me do it differently. How about if I operate A on this vector, but I write this vector as x1 plus 0.2 x2? Can I do that? Right? I mean, there's nothing fancy about it, right? I just, because this vector is x1 plus 0.2 x2, I multiply the matrix first with x1 and then the matrix with times 0.2 x2. But do I know what the matrix does to x1? What does the matrix, what is the effect of the matrix on x1? Remember, the eigenvalue is 1, the first one. So AX1 will be equal to what? x1. And what will be the effect of A on x2? Was the eigenvalue 1/2, if I remember? Right? So it would be 1/2 x2. So there's the answer. Right? So to operate with A on this vector 0.8, 0.2, I can actually plug in x1, because A on x1 is x1, plus 0.2, A on x2 is 1/2 of x2, and there is the answer. So effectively, you know what I have done is, I decompose an arbitrary vector in a basis, all right, in a basis, and then I operate it in each component separately. I operate it on x1, and then I operate it on x2, and then I get my nice answer. Can you tell me anything else that we have done in this course that we have done something similar? Because this is going to be in the exam tonight as well. Where did we decompose things in pieces in doing calculations? What that reminds you? And you can think deeply when we did least squares, right? And orthogonal matrices and projections. When we were doing projections, we were projecting where? To each of the column vectors, so that when they were orthogonal, the calculation was not looking very much different from what we have done now. And if by a miracle I can show you that these eigenvectors are orthogonal also, then it's the same thing. Sort of. In other ways, if those vectors that I was using Q1 and Q2 when we worked with orthogonal matrices happen to be eigenvectors, right? Even better, because they're orthogonal, they're eigenvectors, I can do everything I want very fast. Okay, so remember the relation of the two things. But right now, I just decompose this vector on these two eigenvectors. I can do it in this case, and there's the answer. All right. So let me look carefully now on the effect on this arbitrary vector of the matrix A to a power 99. So I want to multiply this arbitrary vector with the matrix A to a power 99. Can somebody tell me from where this formula came? This part. What have I done there to get this nice formula? Remember that this arbitrary vector, you told me that it was x1 plus 0.2 x2. So what have I done to get A to the power 99 times this vector? I kept operating on this vector once at a time, right? So the first time, remember, operating with A, I got back x1 plus 1/2 of x2, right? And then if I do it once more, what will I get? I will get again x1, and then another 1/2, and keep going. I'm going to get again x1 plus 1/2 to the power 99. Yep? Yes? No? What did you say, sure? Yes, thank you. Any guess in any language is accepted here, okay? Only if it doesn't confuse me sounding like no. Okay, so can you tell me how much is 1/2 to the power 99? Is it a big number? Is it practically 0? What is it? Well, it says there it's a very small vector. So when you operate, you remember I was telling you before, maybe you don't need all the eigenvalues. So for example, here, when I operate with 8 to the power 99, somehow this other eigenvalue 1/2, when you take big powers, disappears because it's a very small number. And the dominant, the steady state eigenvector is only x1. Okay? So I took basically this arbitrary vector, all right? I operated with 8 to the power 99, and effectively, asymptotically, I get as an answer x1. And actually, you know what? You can try something else. You can, I mean, in this particular case, the coefficient there was simply x1 plus 0.2 x2, but you can plug in any other vector. You will see a similar relation when the only term that stays there is the term with the eigenvalue 1, all right? So that leads to the steady state solution to this problem. This contribution dies out because it's a very small number. So I am not going to prove it now, but I want you, because most probably we will forget to come back to this example. I want you to start thinking when you go home after the exam, okay, and convince me that if you take 8 to the power 99 or 8 to the power 100, that asymptotically, this, you know, so as the power increases, every column of this becomes the first eigenvector x1. All right, and this has very much to do with the spectral decomposition theory, right? That you can write every matrix in terms of its eigenvectors, and eventually, because lambda 2 here, these terms die out. The only thing that stays is x1, and this is how the matrix looks like eventually. This is very important, right? Because these iterative methods where you operate with a they come in many, many applications. So in this case, you can actually show that 8 to the power 100 consists with the x1 eigenvector in both of its columns. Okay? In both of its columns. Okay. I'm going to keep clicking extremely fast right now because these slides basically repeat what we said for an n by n metric, so there's really nothing new. So that's the eigenvalue problem for a system with n equations. So you form the A minus lambda I. You take the determinant equal to 0. You solve it. Let me just put this in parentheses and say the following thing. Do not assume that when you solve it, you're going to find n distinct eigenvalues and n distinct eigenvectors. Many different things can happen, right? Actually, do not even assume that the eigenvalues that you will get will be real. Okay? So the most difficult case actually to deal, and we will see actually how big headache this can be when we discuss ordinary differential equations near the end of the course. You will see the difficult thing will be to have not n eigenvectors, but less than n eigenvectors. So to have deficiencies of eigenvectors. And that can happen, you know what, when you have a multiplicity of one eigenvalue. Right? So you can have deficiency of eigenvectors. You don't get n eigenvectors. But right now, sort of, we try to forget that difficulty, but it's going to come. I'm going to show you examples of that. All right, so you set the determinant equal to 0. You wish yourself good luck that you can solve it. You compute the lambdas, okay? Okay, keep going. There's nothing that I'm interested. You may say now, how do I compute x? You know, and we already have done this with the row reduced echelon form in computing the solutions of the null space problem. So if I assign you any homework problems or any exam problems, really I want you to formally do through the reduced row echelon form to actually compute the solutions to the null space problem. So that way we demonstrate we learned something in this course. So I have lots of different properties of eigenvectors and eigenspaces. Some of them sort of are not surprising. So let me just rapidly read. It says if W and X are eigenvectors, correspond to the same eigenvalue lambda, then the same is true with W plus X. But you notice it says there with the same eigenvalue lambda. I mean, that makes sense, right? So if AW is equal to lambda times W and AX is equal to lambda times X, if you add the two equations, obviously W plus X is an eigenvector. I mean, there's nothing fancy there. Now, if you take all the eigenvectors that correspond to one eigenvalue lambda of A, the space that you get, the vector space, is called the eigenspace. And again, we will see that it is possible one eigenvalue to actually give you multiple eigenvectors, right? So that vector space that you get, spanned by those eigenvectors, is called the eigenspace of A corresponding to that eigenvalue lambda. All right, and again, these ideas will have significance when we discuss ordinary differential equations. We said already that the eigenvector is determined up to a normalizing constant, okay? So let me do some examples with weird matrices, okay? And I'm gonna start, first remind you all of these interesting matrices we have seen up to now. Remember the definition of a symmetric matrix. Actually, if you have a symmetric square matrix, that's when the eigenvalue problem is the simplest, okay? So that would be an ideal situation. If you have a symmetric case, we will see that we will have eigenvalues that they are not necessarily real, and even the eigenvectors themselves don't have to be real, all right? So this is the case of a skew-symmetric matrix. And then, of course, we have discussed the orthogonal matrices that they are of particular interest to us, right? Because we have discussed about projections, least squares, and so these orthogonal matrices, and they are square here, right? You remember the fundamental property, A transpose equal to A minus 1. In the notes, actually, the notation that I would prefer to use everywhere in the slides, but since I cut it and pasted this, we use Q for orthogonal matrices. And you remember, if the columns of a matrix are orthonormal, Q transpose Q equal to I to start with, but if in addition the matrix is rectangular, then Q transpose equal to Q minus 1. And that's when we call this matrix an orthogonal matrix. And you may say, who cares about symmetric? Okay, we care symmetric because life is easy, but let me just say that in principle, every matrix of real numbers can be written as the sum of a symmetric matrix and an anti-symmetric matrix, okay? I don't know why he used an S there, but it doesn't matter, a symmetric matrix and anti-symmetric matrix. And you will see in many courses, in materials, in fluids, you know, when you learn continuum mechanics, basically, you will be decomposing things to symmetric and anti-symmetric parts because you can do operations separately on each of them, taking advantage of the structure of the matrix. All right, so here is the interesting theorem. The eigenvalues of a symmetric matrix are real. The eigenvalues of a skew-symmetric matrix are pure imaginary or 0. So at least if the matrix is symmetric with real elements, we know that the eigenvalues of that matrix are real, okay? And for a skew-symmetric, the eigenvalues are pure imaginary. All right, so what, you know, you already have seen calculations where we would like to operate on a vector x with some matrix A. So this sort of transformation is very common, right? Everywhere in engineering, you always need to multiply with some operator, so you need to do calculations of the form y equal to ax. So we will do some examples when A is an orthogonal matrix, okay? And a typical, we have discussed a lot of orthogonal matrices. We discussed about projections. We discussed about reflection matrices. What else was that there? Any other orthogonal matrices? All right. We have, here is a rotation matrix, okay? So basically, we take in the plane the vector x, and we rotate it by an angle theta. Okay, obviously, this is an orthogonal transformation, a particular example. I actually am going to pass all this because we already have seen them, right? Actually, this can make a nice exam problem for tonight, but I don't believe it is there. It says the determinant of an orthogonal matrix takes the values plus minus 1. So don't worry, it's not there. Okay? So the eigenvalues of an orthogonal matrix A are real or complex, conjugates in pair, and have absolute value equal to 1. There is way too much information in that statement. It says they can be real, all right, or complex conjugates. So which means if you get an eigenvalue that is alpha plus I beta, where I is the complex number, alpha minus I beta will also be an eigenvalue of this problem. And it says all the eigenvalues have an absolute value of equal to 1. Right? So we need to do some examples. A transpose has the same eigenvalues as A. You can take AX equal lambda x, take the transpose, you will convince yourself of that. All right. Let's consider a projection matrix, right? We discussed this in the last few lectures. So we are projecting to some column space of a matrix, or to a line or anything like that. So in this case, you can think you take this projection to this line. Looking only at the picture, please don't read what it says there. Look at the picture, and can you tell me what are the eigenvalues and eigenvectors of a projection matrix to a line? So if P projects to a line, what are the eigenvalues and eigenvectors of P? So take different vectors x, right? And try to see if there are any special orientations that are maintained when you operate with a projection matrix. So let's say we're projecting on this plane here. If a vector is already on the plane, what is the operation P on any vector on that plane will do? It will keep that vector as is. So P times x1 will be equal to x1. All right? So already we identified that one of the eigenvalues is lambda equal to 1, right? And it basically, if this is, let's say, the projection to some column space, right? It fills basically, so lambda equal to 1, it fills the column space. When it operates on any vector in that column space, those vectors remain unchanged. How about now if you take the orthogonal complement of the column space and you take a vector x2 that is perpendicular to that column space? What is the effect of the projection matrix? So when I operate on x2 with P, what does it do? It will basically what is the orthogonal complement of the column space? How do we call that space? Which one? So that's the left null space, okay? But here, if these are orthogonal complements, right, the only thing they share together is the 0 point, right? So the projection P of x2 is 0. So effectively, we have an eigenvalue equal to 0, which doesn't look very good because you remember we said we're looking for non-zero, right, eigenvalues. But you notice the eigenvalue is 0, but that doesn't say that x2 is 0. All right, x2 is not 0. Okay? So effectively, with this projection matrix, I can fill the whole of column space and the whole of null space for this particular problem. So let me see if there is an example. So let's consider the following example. This projection matrix 0.5, 0.5, 0.5, 0.5. You can verify that lambda equal 1 and lambda equal to 0. You remember this is projection in a line, right? And we said projection in a line. You remember how the projection matrix looks like for tonight? If you project on a line, what's the rank of the matrix that projects on a line? 1, okay? So basically, both the column space and the row space are spanned by the same vector, which is 0.5, 0.5. So the eigenvalue here is 1, and the eigenvalue is 0, right? By default, I mean, this is a projection matrix. This is what you get, okay? And the eigenvectors for the column space is 1, 1, which is basically this vector here that generates the projection, right? 1, 1. And the null space is 1 minus 1. Okay, 1, 1, and 1 minus 1. Okay. So this matrix that you see, this particular, it's important because you notice the sum of the, if you take every column and you sum the elements in every column, you get 1. This is what is called a Markov matrix. And for those who would be interested to explore, if you never heard of Markov matrix, it's very common in probability theory. So when I say it sums to 1, is because probabilities need to sum to 1. So this is fundamental matrix in a lot of application. It is singular because lambda equal to 0. And you know, if lambda equal to 0, you are not going to be able to invert this matrix. Because can you see actually, if a matrix A has an eigenvalue lambda, A minus 1, what do you think? What eigenvalues we have? I mean, we discussed before the powers. I can start taking powers backwards, actually. What eigenvalues do I expect for A minus 1? Well, so it will be 1 over lambda. And in this case, because lambda equal to 0, this is a singular matrix. So this particular matrix is a Markov matrix. It's singular. And also, it happens to be symmetric. And because it's symmetric, and we will prove this most probably on Monday, it comes out that for the symmetric matrix, these eigenvectors are orthogonal to each other. I mean, in principle, right, geometrically, you expect it to be orthogonal because effectively, you can see the geometry here, right? x1 is here, x2 is orthogonal to x1. So this is represented with the two eigenvalues because those two eigenvalues, they span basically the two orthogonal complementary subspaces, the null space and the column space drawn here with these two lines. Okay. So if you take an arbitrary vector, you remember, and actually this may be handy even in the exam again today, if you take an arbitrary vector in the plane, what I can do is I can write it as a sum, as a combination, a linear combination of a vector that is on this line and a vector that's on a perpendicular line. Can I do that? Because they span the whole of R2 space. So I can take a vector that I write it as, I can take the vector 3, 1, and I can write it as 1 minus 1, which is the null space eigenvector, and I can write it as 2 times the column space eigenvector. And if I operate with a projection matrix P on V, what is the effect of P on this vector? To the null space eigenvector? What P does to this? So when you project something that's orthogonal to the subspace, where does this take you? 0. And this is obviously in the column space, right? What happens to that vector when you project it with P? Nothing. It stays where it is. All right? And again, you can see that here the calculation of PV for this particular projection matrix. All right, so I can do this with reflection matrices. They are also interesting matrices. You can see actually the columns here are orthogonal, right? It's a typical orthogonal matrix. So the eigenvalues are lambda equal to 1 and lambda equal to -1. Geometrically, if you want to get a sense of what a reflection matrix does, if you reflect vectors with respect to this line that you see here, if you are on that line, nothing happens to you. So R on operating on x1 gives you x1. All right, so there must be an eigenvector that spans this line. But if you are, on an orthogonal complementary space, right, x2 would be reflected basically to -x2. That's what reflection means, okay? So, and that's what actually leads to this eigenvalue that you see there, lambda equal to -1. So the eigenvectors are basically, for this matrix, are 1, 1. You can test it. Is 1, 1 an eigenvector? If you multiply this with 1, 1, you get 1, 1, right? Times 1, that's good. Is 1 minus 1 an eigenvector? If you multiply 1 minus 1, what do you get? You get -1 and 1, which is -1 times this. So this is an eigenvalue, and 1 minus 1 is an eigenvector. And actually, should not be surprising because, when we define the reflection matrix, you can write any reflection matrix actually with this nice formula as 2 times the projection matrix, P, minus the identity. So effectively, you know what? What were the eigenvalues for the projection matrix? Remember from the previous slide, what did we get? It was 1 and, for the projection matrix, what were the eigenvalues? 1 and 0. So you know what's happening when you have now, you have a matrix that you take 2 times the projection minus the identity. What do you think, when you remove the identity, what do you think does to the eigenvalues and to the eigenvectors? Think of AX equal lambda x, right? And then you want to find the eigenvalues and eigenvectors of A minus the identity matrix. What will do to the eigenvalues and eigenvectors? You can write one equation down in a piece of paper. So if you shift the matrix by the identity, in this case, just simply by the identity, what happens to the eigenvectors? Again, think the definition of eigenvalues and eigenvectors, the eigenvalue equation. AX equal lambda x. If I shift A and I want the eigenvalues and eigenvectors of A minus I, what will be the eigenvectors of A minus I if I know the eigenvectors of A? I on x gives me x. So if I shift my A by I, what happens to x? It's still an eigenvector. And what happens to the eigenvalues? If instead of A, you use A minus I, what can you say about the eigenvalues? They are shifted by how much? 1. Thank you. There was a violent 1 for those who are listening to the tapes, right? So my students are very excited about 1s. Hopefully, today we will have better grades in the exam. Okay, I'm just kidding. Come on. All right. A few facts. And I will not prove them yet, okay? But you can actually, we do know everything we need to actually prove them, but I will refer to these things later on. If you take the product of the eigenvalues, you get the determinant. Okay? And again, you see this amazing thing, right? The determinant is related with pivots, and the pivots are related with elimination. And now the eigenvalues that come out of nowhere are related to the determinant. So all of these things somehow they are interconnected. An accident, right? It's not an accident. And then if you take the sum of the eigenvalues, all right? This comes to be equal to the trace of the matrix. So if you have a simple matrix, right, and you sum the diagonals, the trace, you can actually start guessing what the eigenvalues will be, and you can test them, okay? So you don't really have to solve any characteristic equation because the sum has to be equal to the trace and the product has to be equal to the determinant, so that's a very easy way to go about. I just want to show you one rotation matrix, 0, -1, and 1, 0. So obviously, the two eigenvalues, the trace is 0 here. If you sum the diagonals, the trace is 0, and their product is equal to 1. All right, and you say, how can they be lambda 1 and lambda 2, how can they be equal to 0 and the product equal to 1? Well, they can if lambda 1 is equal to I and lambda 2 is minus I. If you sum them up, you get 0. If you multiply them, you get minus I squared, which is equal to 1. So if you solve for the eigenvectors for these lambdas, the eigenvectors for this rotation matrix, they come to be complex vectors, all right? 1i and I1. And you may say, do we really care about complex vectors and all of these things? Well, just so you can start thinking that why you actually need them, I can tell you everything on the fast Fourier transform is about using matrices with complex components, basically. Everything, all right? So everything in signal processing basically utilizes this type of vectors that you see here. So if you say, no, I only want to stay in real eigenvectors because I work in fluids, no, you're wrong, because actually when you're going to use the fast Fourier transform tomorrow for something else, you realize that somehow this is very, very important. So hopefully I will take the time and discuss this in a forthcoming lecture. All right. So if we apply this idea that the product of the lambdas gives you the determinant, and the the sum gives you the trace. So here is one example, okay? So actually, in this example, you don't really have to solve anything. Look at this example, 3, 0, and 1, 3. Can you guess what the eigenvalues are immediately? Because it's an upper triangular. I mean, the sum of the eigenvalues has to be 6, right? The determinant of this is 9. So what gives you 6 and 9? It has to be 3. So this is sort of a very weird example because it only has one eigenvalue. So that's bad news. So do you expect to get 2 eigenvectors from one eigenvalue? So we're going to have deficiencies of eigenvectors here. And that has implications on what type of calculations we can do with this particular matrix. So if you calculate you plug in lambda equal to 3, and you try to look for x's, you're actually getting only one eigenvector, which is, you can immediately see from this equation here, you can see that the eigenvector you get is 1, 0, okay? So we have a shortage of independent eigenvectors, okay? We have a shortage of independent eigenvectors. You know what? Because I have 5 extra minutes and I know the other class is Friday, most probably will not even show up. Let me, it's Friday, it's it's Notre Dame. There's a football game and, So let me put all of these things up because you will need to use this in your homework. It will be a summary of the lecture that I'm going to give you on Monday. So let me go rapidly through this and I'm going to post the slides today. If you have a matrix that has distinct eigenvalues, all right, you can show that in that case you get distinct eigenvectors. So if you take all the equations for all the eigenvalues and eigenvectors, you can write them actually in a matrix form where that matrix X, each column contains one of the eigenvectors, all right? So AX equal X times lambda, and that lambda is a diagonal matrix with each element in the diagonal being the eigenvalues. So again, this equation is all of these equations put together in a matrix form. AX equal X lambda. So if you have independent eigenvectors, actually you can invert X, all right? And you can show that lambda is X minus 1 AX. So effectively, by operating with X minus 1 on the left and X on the right, you can do what to the matrix A? You can diagonalize it. So you can take something that looks very complete. It's like you do change of coordinates. And actually, you do change of coordinates. Instead of working on X, Y, and Z, your new base now, you know what it's going to be? The eigenbases. You work in the coordinate system defined by the eigenvectors. And in that coordinate system, the matrix A has actually become a diagonal matrix. Right? It's your decision. Do you like something that is a full matrix or a diagonal matrix? Obviously, you like a diagonal matrix. And there is the benefit. If you understand this calculation, when you want to calculate A to any power k, guess what the answer is immediately? Right? If A is X times lambda X minus 1, you can actually take A times A times A times A and substitute this in your A, and you will come up that A to a power k is X lambda to a power k X minus 1. No calculations to be done. And actually, when you want to calculate A to a power 100, if some of the eigenvalues are less than 1, what can you do to those diagonal terms lambda to a power 100? You say very small, very small. And if you use this nice formula, you know what? You remember when I showed you how to calculate 1 to a power 100 before? You will come up with that answer. OK. So the thing that we need to do basically often in engineering applications is to calculate, to solve this iterative problem. So basically, we have some vector u, and we start with some, let's say, vector u0 at time 0, and we want to keep applying this calculation, a times u0 to give me u1, a u1 to give me u2, etc. I mean, if you have any dynamical problem, this is what you do, right? You move forward in time by operating, in this case, with some metrics. The question is, can you do this calculation using this eigenexpansion, this equation here, that A is X lambda X minus 1? Can you do this using that to calculate how this sequence will look like? And the answer is yeah, very simple. You can analytically show immediately, right, that UK is AK to a power times U0. Can you see this? I mean, I start with U0, then I go to A U0, then I go to A squared U0, to A cubed U0. So UK is A to a power K U0. And what is A to a power K is that. And I wanted to write it explicitly, and I'm going to stop there when I'm done that. If somehow your initial state U0, you write it in the in the eigenvector basis. So if you write U0 initially as C1 times X1 plus Cn times Xn, then this calculation for UK is effectively operating on with A on X1 and X2 and Xn, and UK comes to be C1 times lambda 1 to the power k X1, sigma n times lambda n to the power k Xn. So basically, if you know how to write your initial condition in terms of eigenvectors, you have a general formula in any way you want to see it for computing the state at time k. You can use this in matrix form, or you can use this written. Basically, this is the same calculation written explicitly in terms